We're in the middle of a discussion about substitution reactions, and we've described two basic mechanisms, one stepwise, which we're calling SN1, and in this mechanism we lose the carbon iodide or carbon leaving group bond first, and then we make the bond with the nucleophile. So here iodide is the leaving group, and Cn minus is our nucleophile. And we end up swapping out the leaving group, the nucleophile for the leaving group. We talked about how the reaction proceeds through two steps. You have an intermediate, it's a carbocation. The first step is the one that requires the most activation energy, so that's the rate determining step. And the rate law, as we said, would be first order in starting material methyl iodide, but zero order in nucleophile because the nucleophile isn't involved in the rate determining step. This is a different, perhaps, form of a rate law than you've seen before. The rate laws, integrated rate laws you've seen before are probably of the form concentration of, I don't know, starting material A equals whatever you started with times the number E to the minus KT. This is a law for the concentration of something as a function of time. We're just doing rate as a function of time. And these two are basically totally compatible with each other. You can do some calculus and get this one out of that one, but we won't worry about that one. Some of you may ask, how is it possible that this reaction be totally independent of nucleophile? The answer is it's technically not, but that is only true at really, really small concentrations of nucleophile. If you want to know more about that, we can talk about it. Why don't you come to my office and we'll discuss it. We'll show you a more detailed rate law that simplifies to this when the concentration of the nucleophile is high. We talked about stereochemical consequences of this mechanism and how because of the planar carbocationic intermediate, you should expect to get both enantiomers, or rather both stereochemical configurations if you make a stereocenter. The reason for that is that we can attack from above or below, and you can't prefer one versus the other. The lobes of the empty p orbital in that carbocation are the same above or below in terms of how the nucleophile sees it. And so you would expect to get a one-to-one mixture of stereochemical configurations. In this case, it's a racemate, two enantiomers. If there were some other stereocenter in this molecule, that one would stay unchanged, and we would simply get both configurations of the stereocenter here. Now, our second mechanistic hypothesis was what we're going to call a concerted hypothesis. That is, the nucleophile attacks at the same time as the leaving group is leaving, and you go through a transition state, which looks like this, but because, and in terms of the carbon, it sort of looks like a carbocation, it's planar, but because the nucleophile and the leaving group are both involved, as one leaves, the other comes in, and therefore we never have an intermediate that's identical on both sides. Yes?
For transition states, why exactly would have partial negative bond on donating electron?
For a transition state, why is there partial negative on each? It's because when the iodide leaves, it's going to leave as I minus. As the nucleophile's coming in, it comes in as Cn minus. At somewhere in between, we've got a partial bond here and a partial bond there. Overall, we've got one negative charge for the complex, but it's if there's no bond at all, we have a full negative charge on C. If there's partial bond, that drops down a little bit. All right. We said that this reaction is concerted. Both things happen at the same time. Here is an energy diagram showing a single step. The rate law depends on both the nucleophile and the alkyl halide. We would say that the rate law is first order in Cn minus, first order in methyl iodide, and we would say second order overall because there's two concentration terms in the rate law. And then we talked about stereochemical consequences of this reaction. We mentioned that when we attack the carbon, when the nucleophile attacks the carbon, it does, oops, that's what we wanted for leaving group, huh? When the nucleophile attacks the carbon, it does so at the backside of the carbon leaving group bond because that's where it most easily accesses the sigma star. We considered the consequences of backside attack, and we showed that backside attack should give you what we're going to call inversion of stereochemical configuration. Br minus was up, the nucleophile replaces Br minus and is down. And then we considered front side attack, which would lead to retention of stereochemical configuration. Br is up, OH is up. Only if you think about the orbitals, front side attack doesn't make a lot of sense because there's small lobes there and there's also a node right in the middle of it. So that doesn't give you the best interaction of the HOMO from the nucleophile with the LUMO from the electrophile. And because we're attacking a sigma star, it makes sense that we break the carbon Br bond. So to summarize, this single enantiomer is the only one we observe for the SN2 reaction. And so in this way, you can tell whether a reaction mechanism was SN1 or SN2 simply by looking at the products. If you have a chiral starting material with a stereocenter where the leaving group is, you have to get backside attack with inversion of stereochemical configuration for the SN2 reaction, whereas for the SN1 reaction, you have to go through a planar achiral carbocation, and therefore you get both enantiomers, right? Questions so far? That's sort of the general picture. I haven't told you anything about what makes one mechanism more favorable than another in a given situation. That's what we're going to talk about over the next couple of days. Well, we're all good? Okay. Yeah, okay, good. Boring 10-minute review at the beginning of class, but it's early, so it's good. I'm trying to decide whether to talk about what favors SN2 versus SN1 before I pull back the curtain and show you a whole other thing that was going on the whole time. So I think we'll pull back the curtain and show you the whole other thing that was going on the whole time. All right. So to start, what I'm going to do is draw or show you in Spartan. That'll do. Yeah, that's perfect. This is our oops, why can't we just, all right, well, whatever. This is our alkyl halide that we drew in our SN2 example. And here I'm going to show you what the HOMO and LUMO are. Okay, so you expect the LUMO to be the carbon bromide sigma star. And for the most part, it is. Do you see how we have, let's see, I can't necessarily point. There's no laser pointer with the Spartan app. Do you see how we've got this large lobe on the backside where the nucleophile is going to attack? We have a node in between the two atoms, and we have some more of it here. Do you recognize that alternating pattern of wave function signs? Okay. So that's a sigma star, but you might be asking, what in the heck is going on here? Why is there LUMO elsewhere? Right? Any ideas?
Molecule has kidneys.
Molecule has kidneys, yes. Yeah, it actually does kind of look like kidneys. So this is where, remember that I said at the beginning we were going to focus mostly on valence bond theory, but we were going to need some concepts of molecular orbital theory as well. These results here are calculations based on MO theory. And what we need to do right now is talk about why some of the LUMO is on those adjacent atoms. And I want to focus your attention on this one on the right. There is LUMO on a hydrogen that is adjacent to where the leaving group is. If we say that the carbon, and we'll adopt this kind of way of talking about molecules, the carbon that's bonded to the leaving group we'll call the alpha carbon. The one that's adjacent we'll call the beta carbon. There are two beta carbons here. They're different. One's a methyl group, the other is attached to a methyl group. So, and we'll call this proton attached to the beta carbon a beta proton. And notice that some of the LUMO is on that beta proton. Also notice that the LUMO is not on all of the beta protons, just on that one. And that's the one that is anti to the leaving group. Okay? So, what's going on here? And remember that, right? LUMO's on a beta proton, but not on all of them, just on the one that's anti to the leaving group. So, how do we rationalize this? And the reason we care is simply because if a nucleophile were to come and approach this molecule, there are multiple places it could attack. A nucleophile could attack at the beta hydrogen, or it could attack at the carbon. You've got a choice. And anytime there's a choice, molecules, as far as we know, don't make choices, and so you've got to consider multiple possibilities. We're going to see that molecules that are good nucleophiles generally prefer attacking the carbon, whereas molecules that are strong Bronsted bases will prefer to attack the hydrogen. And we'll talk about what those things are. But let's account for the weird goings-on of this orbital to begin with. All right? So I'm going to attempt to draw that molecule. I'm going to try to draw it in the same sort of orientation as we drew it in Spartan. Okay. And recall that we had a node here, small lobes here, with a large lobe there. And let's just use our typical colors for the sigma star. All right? No problem there. Now, on the adjacent carbon, we'll call this beta carbon maybe 1, because there's 2 different beta carbons. You can see that this carbon-hydrogen bond is lined up with and anti to the carbon-bromide bond. And in fact, if we were to draw a Newman projection looking down that bond, what we would see in the front here are the hydrogens for our beta carbon 1. And in the back, we would see the Br group here. And let's see, from our perspective, then hydrogen is here and ethyl group is there. You good with that view? Molecule? All right. When we're in this conformation where the beta proton is anti to the leaving group, what happens is that the carbon-hydrogen sigma bond filled orbital can line up with the carbon-bromide sigma star empty orbital. Okay, so this is the filled carbon-hydrogen sigma bonding orbital. We'll put electrons in there. And this over here is the empty carbon-bromide sigma star. Do you remember what term we use for a situation where a filled orbital overlaps with an adjacent empty orbital in the same molecule? Hyperconjugation. We've seen that once previously when we talked about why staggered is more stable than eclipsed, right? And remember what hyperconjugation is partial mixing of a filled orbital, the filled carbon-hydrogen sigma star with the empty, the filled carbon-hydrogen sigma bonding orbital with the empty carbon-bromide sigma star. And you can think of what's going on here in sort of a MO energy diagram like we've done previously. The carbon bromide sigma star would be up here, high in energy. The carbon hydrogen sigma on the adjacent beta carbon will be here, and it's got electrons in it. Okay, and anytime we bring two orbitals together, they mix, and we get one that's lower than we started at and one that's higher than we started at. We've also said that orbitals mix more the closer they are in energy, and these aren't very close in energy, so they're not going to mix a whole lot, just a little bit. So when they mix, we're going to get one that's a little higher in energy and one that's a little bit lower in energy. The lower in energy one we get by adding the carbon-hydrogen sigma bond to the carbon-bromide sigma star. And the higher energy one we get by subtracting or bringing them together with opposite wave function sign. All right? This process allows the electrons that used to be just in the carbon-hydrogen bond to spread out a little bit. So let me show you what this looks like. And we'll simplify this by just I'm going to simplify the molecule so it's easier to draw stuff on. All right, if we added the carbon hydrogen sigma bonding orbital to the sigma star in phase, or rather with the same wave function sign, we would get something like this, right? And we would expect the electrons in the carbon-hydrogen bond to be spread out a little bit more in the direction of the sigma star, okay? So that's the plus combination. So one consequence of hyperconjugation, we'll call this sigma to sigma star hyperconjugation. One consequence of this is that the carbon-hydrogen sigma bond electrons move lower in energy because of partial delocalization. It's not as much of a decrease in energy as you would expect for a full bond, but it does mean that there's a little, that the electrons in this carbon-hydrogen bond are spreading out a little bit towards the other carbon, almost as though you've got a teeny bit of double bond character. The other consequence is that the LUMO spreads out onto the beta proton. And to see why this is the case, remember this is our plus combination. Let's draw what the minus combination would look like. We'd simply bring them together with opposite wave function sign. All right, So what this tells you is that some of the LUMO is on the adjacent carbon-hydrogen bond. Now, I'm not going to ask you to draw what these look like, but I am going to ask you to understand the consequences of hyperconjugation. So first, carbon-hydrogen bonds move lower in energy. Second, the LUMO spreads out onto the beta proton. So take a look at what we've drawn here and compare it to what we saw in Spartan. Pretty close. What we're looking at is the LUMO of this molecule, which you get by combining adjacent carbon-hydrogen bonds with the sigma star. Now, again, I'm asking you to just pretend like the left-hand side of the molecule doesn't exist, because there's some weirdness going on over there that frankly won't have any consequences for us, so we're not going to worry about it. But I do need you to see really clearly that some of the LUMO is out on that beta proton. Questions about that concept? Yeah?
So if it makes the electrons in the carbon-hydrogen bond move to a lower orbital, wouldn't it make the antibonding of that orbital increase? So it'd be harder to break those bonds?
So, right, the question is, if we move these electrons lower in energy, don't we also see a corresponding increase in the energy of the sigma star of the LUMO? The answer is yes. It's usually not enough to change the reactivity of the molecule, but you're right. Yeah.
So the differences that we see when a molecule will attack on the carbon or on the proton is if it's nucleophile or non-state acid?
Base, if it's a nucleophile versus a base, yeah. So because we've said that the LUMO is now both the sigma star and an adjacent carbon-hydrogen bond, then a reactive molecule, which we'll just call a nucleophile or a base, can choose to attack in a couple of locations. A nucleophile will attack there, and when you attack at the carbon, you attack the sigma star, the carbon leaving group bond breaks. Alternatively, a base can attack the LUMO at the beta proton. Now, what do you suppose is going to happen if the base attacks the beta proton? Yeah, a base removes a proton, right? If you remove this proton, then what do you think is going to happen to the electrons in the carbon-hydrogen bond? They're already lined up with the sigma star, right? So they could just dump completely into that sigma star, and then the leaving group leaves. Yeah. If what's on the left happens, we call that a substitution reaction, because we're going to replace the nucleophile, we're going to replace the leaving group with the nucleophile. If we attack the beta proton, the product there is going to be an alkene. Our base will have picked up a proton and the leaving group left, yeah. And we're going to call this an elimination reaction versus a substitution reaction. We're calling it an elimination reaction because we eliminate the proton and the leaving group from the molecule. Yeah?
So, wait, aren't bases nucleophiles?
The question was, aren't bases nucleophiles? The answer is yes and no. What? Okay. So how do you know whether something's a good base or a good nucleophile? Let's talk about it while we're here, all right? The problem is there's some overlapping between those two groups. And so we're going to see a couple of different classes of molecules. We're going to see molecules that are neither a good base nor a good nucleophile. We're going to see molecules that are a good nucleophile but not a good base, and then we'll see molecules that are good nucleophiles and good bases. There's a fourth category out there, but it's kind of we'll save that for later. So what makes a good nucleophile good? In general, good nucleophiles have conjugate acids with pKa's that are greater than 0. Doesn't take much to be a good nucleophile, actually. And there's a lot going on here. There's a whole thing called hard-soft acid-base theory that we could talk about, but we're not gonna. So this general summary will work for us. So what are some things that could be good nucleophiles? Well, you know, sort of go to your pKa table. Acetate or carboxylate anions are conjugate bases of carboxylic acids whose pKa is around 4. All right? So this is reactive enough to be a good nucleophile. What is not a good nucleophile? Well, water. Not a good nucleophile. Of course, water's conjugate acid is hydronium pKa -2. All right? Alcohols in general are also poor nucleophiles because their conjugate acids have pKa's around -2. In other words, the things you learned before about what makes a pair of electrons reactive based on acid-base chemistry, the same kinds of things that are going to make molecules nucleophilic. Also, let's see, on our list of things that are decent nucleophiles, thiols, or rather thiolates, that is negatively charged conjugate bases of thiols. That's a pKa of 8. Let's see, I'm missing a bunch of stuff. Azide N3 anion is, we should put that here, has a conjugate acid HN3, which has a pKa of around 9. Also, CN minus has a conjugate acid HCN, pKa around 9. And let's see, what else am I missing here? Yeah, hydroxide is a good nucleophile. Oops, wrong column, because its conjugate acid has a pKa of 16. Also, alkoxides, conjugate acid, the alcohol also has a pKa of 16. And then one more we ought to think about is just the negatively charged terminal alkyne. We'll call this an acetylide anion. Its conjugate acid, terminal alkyne, has a pKa of around 25. Yeah?
So essentially, all bases are nucleophiles, but not all nucleophiles are bases.
Essentially, all bases can be nucleophiles, but not all nucleophiles are bases. I think not all nucleophiles are good bases. Yeah. So what I will say is that good bases, Bronsted bases, have conjugate acids with pKa's greater than or equal to 16. So here's sort of your dividing line. Here you have things that are good nucleophiles and good bases. Here you have things that are good nucleophiles, but poor or weak bases. Okay? And then the last piece of information that we need to sort of reason our way through what's going to happen is that good nucleophiles attack sigma star at carbon, whereas good bases attack the beta proton. Good nucleophiles give you substitution products. Good bases give you elimination products. All right? Yes?
Does being a good base override being a good nucleophile?
Does being a good base override being a good nucleophile? No, in general, understand we haven't said anything at all about the alkyl halide, and there's going to be some things about that structure that influence the outcome of the reaction. But in general, things that are good bases will also be good nucleophiles. Shall I tell you the exception to that now? Why not? Okay, so think about, let's go back to Spartan and think about, let's now look at the space-filling model of this molecule. And I want you to think about where the sigma star is. Okay, we'll show the LUMO again. Okay, take a look at that, and then we're going to switch to space filling. The proton, the beta proton, is more easily accessible than the sigma star on the carbon. So you might predict that you could bias this reaction towards attacking the beta proton if you used a base that was really bulky or large, such that it really couldn't get in there to where the sigma star is on the carbon. And we'll see then that we have a category of things that you would, based on pKa alone, predict to be good nucleophiles and good bases, but because of their steric bulkiness, they are poor nucleophiles, but still good bases because protons are easier to attack than carbon. One of these is pert butoxide. The conjugate base of T-butanol, pKa of this is 19, a little bit less, even less acidic than a typical alcohol. So you would predict this to be a good nucleophile, and yet it's not, and that's because it's just too large. There are some others that your text will talk about. I won't draw them here, but the basic principle is a sterically bulky base is not a good nucleophile because it's too large to attack carbon. There are a couple others that, frankly, synthetic organic chemists like molecules with acronyms in their names. And so your text author is a synthetic organic chemist, and so they will tell you about DBN and DBU, which are also sterically bulky bases. I'm not going to draw them because I don't want to, and if you wanted to know their structures, you could look them up, and in any case, you're not going to be drawing memorized structures on my exams. But if you see these in practice problems, they're just sterically bulky bases, all right? So, maybe let's use our newfound knowledge to predict outcomes of some reactions. Yeah. I don't know why I'm getting emotional again about chemistry. It's just so beautiful. Right? Maybe I should try that in testimony meeting. Testifying about molecules, right? Okay, so let's just take this simple molecule that we started with. No, actually, we'll go with this one. And let's predict outcomes of reactions based on what we've just talked about. All right. So let's suppose we used sodium as a counter ion to this nucleophile. This nucleophile is called ethoxide. Sometimes people will write this as NaOET, for ET for the ethyl group. All right, so let's go back to our list. Sodium ethoxide should be what kind of nucleophile / base? Both, okay? So, in general, for sodium ethoxide, we want to, and remember, I've said nothing about how the structure of the alkyl halide influences the reaction. I'm deliberately not doing that yet. We'll do that soon. But if you've got a nucleophile that's both a good nucleophile and a good base, you want to be prepared for both substitution and elimination products. That is, you want to be prepared to attack, in some cases, the carbon to create a substitution product, or to attack the beta proton to create an elimination product. All right, so let's do the substitution product first. I also haven't said why these reactions are going through the concerted mechanism where we attack and the leaving group leaves at the same time. We'll get to that too. But for right now, let's just consider the substitution and elimination outcomes. So if I were going to draw a mechanism for the substitution reaction, what do I need to do? Where are my arrows going to go? Arrows start with nuclei. No, they don't start with nuclei. Arrows start with electrons, and they end where the electrons are attacking. In this case, they're attacking the sigma star. It's backside attack with inversion of configuration. So we'll draw the mechanism that way, and to show inversion of configuration, we will put our nucleophile in the down position. All right? Now, elimination products. What's that going to look like? So first, we need to identify beta protons, right? And in particular, we need to identify beta protons that can be anti to the leaving group. Remember that it's only when the beta proton aligns with the sigma star that the LUMO spreads out onto the beta proton. So only protons that are anti to the leaving group will be reactive. So we've got a beta carbon here. We got any other beta carbons? Sure, other side too. And so if we attacked at the blue beta carbon, we're going to get a different elimination product than if we attack at the purple beta carbon. Tell me though, based on how I've drawn this molecule now, where do you predict, which of the protons that I've drawn do you predict to be the one that's going to get removed? The one that's going back? Right. If you're struggling to see that, draw a Newman projection looking down the bond between the alpha carbon and the blue beta carbon, and convince yourself that this proton that I'm circling now, the one that's going back into the page, is anti to the leaving group. All right? So we could show the base now attacking that proton, electrons kicking down into the sigma star, and the leaving group leaving. And that would give us an alkene product. Are there any stereochemical issues I need to take care of here? Any stereoisomers possible around that alkene? Nope, two of the same thing on one of the sides, right? There is no cis or trans for that kind of alkene. You see that? Yeah.
And the nucleophile is more likely to attack the hydrogen that we are attacking it on because on the other side, the methyl group makes it sterically hindered, right?
So the question is there selectivity? Does the nucleophile prefer to attack this one because it's less sterically hindered than this one? That's a great hypothesis. It just turns out not to be the way things work out, for reasons that we'll talk about a little bit later when we talk about the structure of the alkyl halide. But for now, it's enough to see. For now, it's enough to see that we have the possibility of attacking that other beta proton too. Again, as the molecule is currently drawn, it's the proton that's going back into the page that's anti to the leaving group. So we could draw the mechanism this way. And let's see. Doing that would give us, no? That elimination product. Okay. Fine. Are there stereoisomers possible there? Okay. Is it possible for me to get the other stereoisomer? Remember, the proton has to be anti to the leaving group for it to be reactive in an elimination reaction. So you're thinking, no, because as drawn here, this is the only one that's anti. Okay, let me ask, can you rotate around the bond between beta and alpha carbons here to make it so the other proton can be anti to the leaving group? Sure. In fact, we could redraw the molecule if we rotate around the alpha to beta bond. Whatever. Such that the proton that used to be up is now anti to the leaving group. We would end up with, whoa, that's gross. There we go. Shape like this, right? And then the base could come and remove that proton that's now anti to the leaving group. And we would get, in that case, not the trans isomer. Do you see how this methyl group is on the same side of the molecule that this methyl group is? And as the double bond forms, yeah, they're going to stay that way. So then we're going to get the cis isomer. All right. So one starting material, one alkyl halide, one nucleophile / base, 3 products. And it will get worse. Are there 4? Oh, yes, and I can't count, right? There are 4 products. 1 substitution product and 3 elimination products. All right, yes?
One more time, how do we know that the ethoxide is a nucleophile base?
Right, how do we know that the ethoxide is both a good nucleophile and a good base? Just based on the criteria I gave you, they're conjugate acids. Good bases / good nucleophiles have conjugate acids with pKa's greater than 16.
So its conjugate acid would be like ROH.
Uh-huh,
Okay.
yeah.
Okay.
So on the other hand, yeah.
I was just, I think I'm missing something. Can you explain why that alpha carbon is stereoisomer on that third one? Because I thought if you had a pi bond, it couldn't be a stereoisomer.
Yeah, this is a stereochemical definition. Stereoisomers is a term that means same connectivity, different shape. There's 2 kinds of stereoisomers. There's enantiomers, which are mirror images of each other, and then everything else is diastereomers. Yep. Yeah, there's no stereocenters here, but the double bond does create a situation where you can have stereoisomers, cis and trans, E or Z, and these 2 are diastereomers of each other. Right, other questions? Yeah?
What about that big long side chain that we weren't dealing with on that first molecule?
The big long group that we weren't dealing with on our first molecule, actually this is that molecule.
I mean the one you modeled in Spartan.
Yeah, the one in Spartan is actually that molecule. The thing is that they've drawn it for you in a conformation where if you look, this was blue beta proton, this is purple beta proton. In this conformation, none of the beta protons are anti to the leaving group. Had we rotated around this carbon-carbon bond, we could get either of those beta protons anti to the leaving group. Okay, other questions? Oh, you're confident, are you? I'm sorry, that was much too evil a laugh. Yeah?
So say you place one of those hydrogens with, like, in ethyl groups, but you have 2 different groups across that pi bond, but would you not be able to form a bond to get, like, different stereoisomers?
Okay, yeah, the question is, what if one of these 2 hydrogens were a methyl group
Or, like, ethyl groups?
or something else?
Yeah.
Yeah. Yeah, if you only have one beta proton on that side anyway, then there's only one possible elimination product. And actually, that can be a great way for me to test whether or not you know that the proton has to be anti to the leaving group, to see if you get the stereochemistry right in this situation. So, go ahead for your homework and draw me, the elimination product. You don't have to worry about what the base is, just draw the elimination product that you would get from that molecule. Okay? All right. That was fun. Next time we're going to make it even worse.